Welcome, everybody. I'm super pleased to introduce this science visualization team that comes to us from Bremen, Germany. And I'm incredibly grateful for the rain you bring. Thank you so much. California needed rain so bad, and we have it coming down like there's no tomorrow.
And it's typical weather in Bremen.
It's typical weather in Bremen, so we appreciate having you here. I met the team at Ars Electronica, and we were talking about STEM to STEAM. So of course, a big part of what we do at ArtSci here at UCLA is introducing that A into the STEM. And talking to Bianca here, I just got so very excited because in addition to doing the science communication work that she's involved in at the Fraunhofer in Bremen, she also works and has worked with some dance projects and in the background also about interspecies communication. So our conversation became very rich, only for me to find out that, guess what, they're going to be in Santa Barbara for the Raw Science Festival where they won a prize. So they come here full of great energy. And yes, so I'll just stop right there because Bianca actually will introduce you to their program, after which we have Sabrina and Alexander who's going to help us learn about the MEVIS software. We have computers with the software downloaded. You can use your own. And I think you'll be really happy to get access to this software that they're bringing to us along with the rain. So please give them a warm welcome.
Thank you for this nice introduction. And thank you for having me here. I'm very excited. For me, this is a very special place, and that we have a chance to present our projects here and to discuss our thoughts and ideas. I really like that, so thank you. My name is Bianca HOFMANN. I realize projects to involve people early in scientific topics and future technology, thus making the implications for society understandable. In the last couple of years, I expand my activities where science meets the arts, involving the next generation and exploring flexible forms of approaches in science communication. And with me is Sabrina HAASE. She's sitting there. It's a mathematician and a coordinator of research and industry projects. For many years, she has been leading the educational opportunities Fraunhofer MEVIS provides to young students. For example, the STEAM imaging project, we will go in some details. And also Alexander Köhn, and he drives with me our science communication projects. So at Fraunhofer MEVIS, we are an institute for medical image computing, and we develop real-world software solutions for computer-aided medicine. The goals of our work are to detect diseases earlier and provide reliable, more reliable, customized treatments to each patient, and also make the therapeutic success measurable. And to give you a brief idea what this means, only 90 seconds, we will go into the details later in the workshop. I show you a short movie.
The entire body is scanned with X-rays into over 2,300 image layers. The skeletal bones absorb radiation and appear as bright structures in the CT image. For this special type of X-ray imaging, called angiography, doctors need to inject their patients with a contrast agent, which absorbs the radiation from the CT scanner and makes blood visible in the vessels. The trachea appears as a black hole over the jawbone. Above it is the cervical vertebra. The arteries appear as red dots on both the left and right sides. In medical images, vertebrae surround and partially obscure the arteries, impeding the examination process for doctors. Image processing techniques separate vessels from bones and show them three-dimensionally in red. When examining a patient with suspicions of vessel constrictions called stenosis or balloon-like bulges called aneurysms, doctors perform CT angiography. This method also helps physicians plan necessary catheter treatments or surgeries for patients.
So in our science communication, we want to remove barriers that prevent people from interacting with difficult health topics. We are focusing on the clinical impact of new technologies and their underlying math, physics, and computer science. We have developed several communication formats that express the value of our R&D to the public and encourage people to engage with medical technology topics in depth. A strong focus is the engagement of the coming generation. I am convinced that we need to deeply involve not only the public, but foremost young people, and let them actively discuss science and the development of new technologies. Our research is affected in many ways by the fact that the developments in medical technology are changing our everyday lives in increasingly shorter innovation cycles. The rise of digitalization, big data, and AI demands immediate discussion of the implications for the society that needs to be widely understood. With Sabrina HAASE, I designed an artist-in-residency project called STEAM Imaging as a conceptual framework for fostering meaningful collaborative engagement of scientists, pupils, and an artist to break down disciplinary boundaries and explore flexible forms of learning and cooperation. Hands-on projects in the spirit of makerspaces for the next generation have a long tradition at Fraunhofer MEVIS. We place a lot of trust in the young talents, connect them with researchers and with the institution's research, provide them with concrete knowledge so that they can take actions themselves. For us, expanding these proven workshops to an artistic level challenged the participating scientist on a personal level. So what did we want to reach by expanding a STEM workshop to a STEAM workshop and integrating the arts? The shift in science toward the economic output became sharpened through big data and AI. The focus changed from the fundamental understanding of active basic principles of nature to approximations and predictions based on huge amounts of data and statistics. This influences the idea of our future. We need to rethink the pure economization of science and knowledge and have a look at the societal, ethical, and ecological effects of science and tech. What is a scientific success? Especially computer science is challenged to integrate other professions like art, ethics, law, philosophy, to develop a responsible attitude towards new technologies. A well-rounded, open, lively spirit does not emerge from the reproduction or recombination of existing knowledge or achieving the goals of others. We are responsible for our own thoughts and actions and for taking risk, for serendipity, and find something we so far had not known. So with our STEM workshops, we usually wanted to foster the engagement with and ownership of new technology and the development of new formats in science communication. And we want to inspire pupils to learn about STEM topics and their meaning for medicine, and also being role models. In the field of medical technology, we are accustomed to working across disciplines. But what did we want to reach by integrating the arts and pupils? What were we looking for? To answer that, we have to ask ourselves, what is the aim of our educational efforts? To nurture talents, to promote and support intrinsic motivations, to learn and practice scientific thinking, to raise responsible members of society who strive for a good life, or produce people that fit the needs of the job market. On our current path, we are at a point where test and goal-oriented education has limited innovation. So the aims of the residency we created was, so we hope to reach pupils from all dispositions to engage in STEM topics from various approaches. We wanted to show the value of our current science and technology for the art. And we wanted to support an artist to explore new fields and stimulate critical dialogue about the implications for society. And we wanted to inspire scientists to gain clarity and composure concerning their research. We wanted to foster the discussion among researchers about different views based on the spectrum of their expertise. So who was involved in this project? We worked together with a young media artist, Yen Su Chang, within her residency STEAM Imaging. In the first phase of the residency, Yen worked closely for 2 weeks with scientists at the institute. In the second phase, Yen went for several weeks to Ars Electronica Future Lab in Linz, Austria, to finish the installation Whose Scalpel. The performance Whose Scalpel is a fusion of an interactive 3D model of her own heart, movies based on real medical images, and sound. It addresses the future of the human-machine relationship in surgery. The installation raises the question of what humans lose when the computer takes charge. In the beginning, each participant gave a pitch why or he joined the project. We were working with a participatory platform, Confluence, to exchange thoughts and materials, book modules, and discuss. This transparent working style is part of Fraunhofer MEVIS culture. We were exploring the software platform MEVIS Lab, with which we develop assistant tools for clinicians, and you will get to know better later on. And Yen and experts held one-to-one conversations on topics such as AI. We had a session on ethical issues with co-workers and the artist as an open discussion. And the artist twice acquired medical data at the MRI scanner from her own body. Colleagues gave 3 to 5 minute fast-forward presentations of their work. The artist gave a plenary talk for all employees at Fraunhofer MEVIS, and she shared her approach for her current artwork. The team prepared and held the 2-day workshop with Yen for and with the pupils, and Yen presented the outcome, the performance Whose Scalpel, at the Ars Electronica Festival in September in Linz, Austria. So the workshop introduced the pupils, altogether 22 girls and 20 boys, 7th to 9th grade, to a problem-centric approach to learning. The mix of methods of theoretical contributions and explorative teaching activities was an asset to create a holistic experience. The roles of teacher and learner, giver and taker, were changing dynamically. We did also an evaluation of the workshop. If you're interested in, just drop us a note. The workshop included making plaster models of the pupils' hands and scanning these models and also fruits at the scanner, processing the provided medical material and the data from their hands, so the creation of artistic images and short video sequences combined with electronic sounds, ambient noise, or sound from the MRI. We discussed also ethical questions with the pupils and the impact of new technologies in healthcare, and the pupils developed own audiovisual performances. They did presentations at the end of the workshop showcasing their achievements. This was meaningful as a goal throughout the workshop. And now, before I hand over to Sabrina to have a deeper look into the application we worked with the pupils with, Inside, I will briefly summarize the lessons we have learned and our plans for the future. So STEAM imaging for us was an experiment. We realized space for possibilities where what comes next was not predefined. The players and content were selected, but no one knew what the results would look like. What mattered was the collective collaborative learning and openness to what could emerge. It was challenging to boost creativity in the office environment beyond working at a computer. Also, it was not easy to open up and engage in the process within the daily goal-oriented routine of applied science. I missed something, I'm sorry. We would have enjoyed having more time in an atelier-like space for face-to-face encounters to allow playing, fogginess, and collaboration within the cross-disciplinary process, thus having more space for serendipity. Scientists can contribute to developing utopias, neither dystopias nor promises of technological salvation. What do we want to contribute to help face the challenges of demographic change, the digital transformation, and unequal opportunities? Don't we aim to foster the talents and resources of every child? In Germany, the educational level of children is still largely related to the education level of their parents. We have to create new permanent learning environment, both for students and scientists. To do so, we need to expand the range of topics and participants. Now at Fraunhofer MEVIS, we discuss making the residency format more flexible. In the future, not only artists, but also clinicians, ethicists, and lawyers shall be able to work with the researchers. In the scope of science communication, further formats are being developed. For example, a science meets fiction workshop will bring together scientists, representatives from the German film industry, and later pupils. So thank you for listening in this jump into what is MEVIS doing into science communication. Now Sabrina will show you more details about the app.
Should we have to change this here? It's 3? We are 3, yeah. HDMI out, where the blue number is. Oh.
It should be down here.
Right,
Okay.
Okay,
So, is this mic already switched on?
yes, you are good.
Okay. Yeah. Now it's switched on. Great. So, hello everybody. So, as already mentioned by Bianca, so I am a mathematician working in a lot of projects at Fraunhofer MEVIS and also trying to engage the young generation for the STEM topics. So, and I will give you some insights. I will not show you the complete application, but I will give you some insights in what are we teaching there, and also give some motivation of why we are doing that. So this is what we are doing at Fraunhofer MEVIS in images. So we are ranging the whole range from diagnosis to therapy, for example. So here, this should depict the diagnosis. So we are diagnosing our patient with a tumor volume here of 60 milliliters. Given the therapy, like chemotherapy, and taking or acquiring a scan after 4 weeks, we can see on the image that this has shrunken down to 20 milliliters, which is great. So, and this is our contributions. As already mentioned by Bianca, so we are developing software for visualization and analysis of medical data. So we are a software developing institute. So, and what do we want to achieve? We want to support doctors in diagnosing and treatment of diseases. So this is what we do. So we have, for example, images. So everything in our institute starts with the images. So, for example, does anybody know from the audience what imaging modalities we have currently in medicine? Yeah? One, starting with one. MRI, anybody else? CT, X-ray, anybody else? Ultrasound, for example. So I think these are the major ones. So we have many others, and I think the list would be really long. So, for example, PET or anything else. Okay, so we have many imaging modalities. So we are starting getting those images. We are writing code, which you can see here down here. And then a diagnosis, for example, is made, e.g. a tumor-sized calculation. So, and we are not working on a certain organ or a certain disease, just taking a look and getting into contact with clinicians to see what their need is. Yeah, so if the clinician has a need in breast imaging or breast diagnosis, then we are doing this. Yeah, so we are not limited to it. This is the main thing I would like here. So, and now what we are starting with is just simply think about what is an image and what is the dimension. Yeah, so in 2D we have a height and a width, and we brought you photos here from the Bremen town musicians on the left side. So just bringing a little bit of Bremen to here. So these are just photos, so two-dimensional images. Medical images, which are 2D, so for example, one X-ray on the left side, which is part of the leg, and one slice of a computed tomography image on the right side, so one slice through the body. And showing them in 3D just means having a data set like computed tomography, which is a 3D imaging modality, and you can scroll through the images from, in this example, from one ear to the other. And on the right side, this is the 3D visualization of that. So we will see that later on in our MEVIS lab workshop, which we are doing with you as a hands-on. And just to give you an impression how this will look like. So everything behind this is MEVIS lab. Yeah, so this is what you will experience later on. Yeah, so we have merged our teaching material with the application, with the real application MEVIS lab, which we are also using to provide our industry customers with solutions. Yeah, and we here have a brain. Yeah, we can change the contrast here. And we also have the 3 orthogonal slices. I don't know how many of you already have seen such images, but we will definitely see those brain images later on, and you can explore yourself. So coming from 4-dimensional images to, coming from 3-dimensional images to 4-dimensional images, so what does that mean? So we are adding the time into that and having kind of a film. So, but why do we need 4D images? For example, to see how our heart is beating. Yeah, we cannot capture the heartbeat in a 3-dimensional image. And to see if there is a disease of the heart or the heart vessels, you definitely need to have a 4D image or a 4D data set. Just to give you an impression, just to give you an impression on how this would look like. So this is how the heart is beating. Yeah, so we can scroll through the image, and everything around that the heart is also moving. Yeah, we have the lung here, the lungs here in black, and we have the liver down here. So also the liver is moving with the heartbeat. Okay, so. And now I would like to go into some details about which knowledge we can get from these images. So each clinician who is doing, for example, liver surgery is interested in how large is the tumor, where is the vascular system, and am I able to operate this patient? Yeah, so this is the main question, and for this task, we can use segmentation, how it's called in the medical imaging community, yeah, which is a delineation of an image into content-related regions. Yeah, so we are delineating it, or have more automatic methods, which I can show you later on. And we would like to quantify which part of the delineated image is the liver, the tumor, the vessels, and give them a measure. So there are basic segmentation methods. So these are just a few of them. So on the right, on the x-axis, we have the grade of automation, and on the y-axis, we are ranging from pixels to regions. So, and the three which I wanted to show you here are the manual, the live wire, and the region growing method, and explain what difficulties we might have with those. Yeah, and you always have to keep in mind, so this is also our material we are going through with the pupils, yeah, with the young students. So later on in the MEVIS Live workshop, we will also doing some segmentation. So this is why I'm explaining this also now to you if you haven't heard it already. So we have here a brain, and in this brain, we kind of put an artificial tumor, a heart-shaped artificial tumor, because we think that it's easier for the pupils to handle. Yeah? So that if we have an artificial tumor here, yeah? Even our younger students, so if you say them, okay, that's a tumor, so it's kind of difficult for them. So we introduced this artificial one here in this data, which of course is not reality. So how do clinicians do it in the clinical routine? So clinicians who do not have any software support, what they have to do is they have to delineate the heart. Oh, that's too bad here. So I think they do it better than me do now. Yeah? They have to delineate the structure they are interested in on every slice, which is kind of tedious. And also, as you might see it here on the screen, it's not that precise. Yeah? And every physician would see the edges at different parts of the image, because the human brain and the human perception of gray values is very difficult, by the way, which is also part of this application, but I don't show it now because it would take too long, but we also explained about the human perception beforehand. Yeah, so this I would have to do. We can calculate the volume, and here it is. Yeah, so I have not delineated now on every slice, but give you an impression of what clinical routine currently is if there is no software support. So now going to the next automation grade. So we started with the manual, which is not automated at all, and now going to live wire. So what is live wire? For our young students, we call it intelligent drawing, and you may know this kind of method already from Photoshop, or I don't know. The user clicks in the image and the spots are connected automatically. Yeah? This is our image, and we want to delineate this liver, which is this light gray part over here. So, but how does the computer know not to take the red line, but the green line? So before drawing this, this path, a gradient image is calculated. So having a look from each pixel, or voxel in 3 dimensions, looking around and collecting the gray values of this neighbor and computing the differences. So, and this cost image, this is bright at the edges, as you may see here, and dark in the homogeneous surrounding. And what the computer then does is take the lowest cost path, so take the brightest path on this cost image, which is here in the middle. So it doesn't take the red path, but instead the green path, because it's brighter on the cost image. So, and how this would look like, I will show you now. It's the same example. You can just click, and the computer knows where to put the path between 2 points. So, and you saw that's more precise, and I'm really faster with this one. Yeah, so, but however, you still have to do that on more slices to cover the whole three-dimensional tumor volume. So, and the last method I would like to introduce to you is the region growing method. So it's working on regions, as the name already introduces, and has a really high automatization grade. So how does that work? So given a seed point in your area of interest, the algorithm looks also at the neighbors. And you can define, you as the user, or we as developer or researcher, we can find some correlation or some characteristic, some similarity measure of which pixels shall be included and which don't. So for example, grayscales are usually used, and a variance of 20% or something, or a difference of 20% in gray value. So this is a common threshold for this. So starting from this point, and this is an example of a segmentation of a vascular tree. So coming from this pixel, we look at the surrounding and all surrounding pixels. So this is just a two-dimensional view, but also in three-dimensional, as also indicated above. And we are stopping when it's black or dark. The gray is darker than the ones we defined. And this method, or with this method, you are able to segment a whole vascular tree. Yeah, so this is really great, I think. So, and this is an example of the liver again. In the liver, as you might know, we have 3 vascular systems. So, and we are depicting here 2. And only 2 seed points are needed for this. So, and how does this look like in our application now? We call it inside because it gives insights to medical imaging. So how does this look like here? So just giving the algorithm a seed point, initialize everything, and we're done. Yeah, so we're done also in 3D. So, and this is really fast. So the algorithm maybe is not perfect, but it can be trimmed so that it does the job it should do. Yeah, so changing parameters, for example. And also, if you would have given this example to 2 people, the differences in the volume they were calculating is, in this example, for the region growing, it's 0. Yeah, because the algorithm usually does what it does. So unless somebody is clicking outside the region of interest, of course. But usually this should not be done. So for the other parts, there are large differences between clinicians. And this is why we try to automate those algorithms where possible. So in some cases, it's not possible to have such an automated algorithm, and this needs some help of the physician, so some interactive method. But we try to give our best on that. And we hopefully can see afterwards in the workshop of how well or this can be done or not. For some examples. Maybe we are using the manual then. Okay. So I think this was the insight I would like to give you into our Inside program, and we should now hand over to the workshop part, which is an interactive thing. So, and you might ask, okay, so Sabrina just told me this is the MEVIS lab, but this is quite an application, could be anything. So how can I see that this is MEVIS lab? Alex, could you quickly help me to step? So I think I have to go. So we are using Alex's computer here, so this is why I need his help. So usually I can do this on my own.
So.
Okay. Okay. So this was what we just saw was a web application of MEVIS Lab. Yeah, so we think about bringing this to the web so that it is accessible for kind of everybody or everybody interested. And we also hope that it can be used, for example, for online courses, also maybe here in the US for a summer school, or I don't know. So, but it's more flexible than to install the whole application on every PC. Yeah, so it's up to you. Yeah, so there is a public version of MEVIS Lab in the web. So it's www.mevislab.de. Yeah, so I will explain this in a few seconds. Yeah, so you don't have to open anything right now. So I just want to show you how this web application we saw connects to MEVIS Lab, and afterwards, of course, you are all welcome to join the hands-on. Yeah, so just giving you an example. So the web application, so the network which is behind that, so this looks like this. And you can see that if I would drop this here off and going back to the web application, you can see that we don't have any three-dimensional viewer anymore. Yeah, so this is the relationship. I changed something in this network, which I will explain later on how this works. So, and if I'm reconnecting, it's there. Yeah, so this is how you can interactively change something also in the web application or in every application done with MEVIS Lab. So now on your desktop, or maybe I should jump into a short description of what we are doing now for the rest of the workshop. So what we are doing now is I will give you a short introduction into MEVIS Lab. So this is the first thing, so that you can get familiar with those stuff. And afterwards, we will develop a clinical application with you. And Alex will show you here on the computer, and I will go around and help you if some problems occur. And in the last part, we will give some insight into how MEVIS Lab can be used for artistic exploration. And be surprised what this means, but I think it will be great. Okay, so now coming back to MEVIS Lab. On your desktop, there should be a simple logo, like this one here below, just called MEVIS Lab 3.0.1. Alex, may you go around and check? So there are maybe several.
Use the one with the red arrows without the black on it. Yeah, they all are the same in the end, but one always got one. So with the 3 arrows.
Yeah. So the blue sign, which some red arrows on it, and no bug. Yeah, so it should be a window like this, not very similar because we are here on Alex's laptop and he has pre-configured it. So this should be down there. Okay. For those who already have opened, we have this white box here on top of the screen. So this is called search modules. So you can type local image here and select it either with your mouse or with your up and down keys on your keyboard and enter. So does everybody has such a module? Okay, so we call it module. So, and why do we call it module? Because it encapsulates a certain functionality. Yeah, so it is reusable, and for example, this one encapsulates loading an image. If you are clicking on, we call it connector, just click on that. And I hope that your output inspector here is open. Yeah, you can scroll also with the up and down keys through the brain. Up and down keys of the keyboard. Yeah? So we can go from the left to the right ear and back, visiting the eyes and the nose. Okay, so everybody at this stage? Great, great. And then we are taking another two of those modules, namely a view 2D, a view 2D, and a view 3D, how they are called. And you must know that the data flow in MEVIS Lab is always going from bottom to the top. Yeah, some other applications going the other way around, but in MEVIS Lab it's always going from down, from the bottom to the top. And when you hover over this image or over this connector, so this triangle here, it tells you the size of the image, which is now connected to this output. Yeah, just hovering, not clicking, just hovering with the mouse and waiting. So it says this image, which we are have now connected, this has a size of 109, 91, and 80 voxels, and the type of the data which is included here. So now we are dragging from this triangle, and you are only allowed to connect triangle to triangle. And you see there are also other things, so a half circle and a square, but triangles only to triangles. So we are connecting, so just click your mouse here and drag it to another triangle, for example, the triangle of the view 2D. And double-click on the view 2D, and with the double-click, you can open the panel, we call it panel, of the respective module. And we should now see here the same image which we just saw in the output inspector. So I just said triangle to triangle and half circles and squares, so, but what is it? What is transported via this connection? So via the triangle connection, images are transported. Yeah, so every triangle you see, and you will see, this always is an image. If we would have those squares over here, those squares transport data structures. for example, lists of points or something else. Maybe we see that afterwards. For the moment, this is not that important. And the half circles, so this will be used afterwards for visualization purposes. And we will learn about this maybe later on. So now connecting the triangle, also with the 3D triangle, and giving him a double click. So now we see the brain in three-dimensional images. And I don't know if this is feasible with the Mac. So usually with the right mouse click, you can change the range of gray values which you would like to see. So in summary, this is changing contrast. Yeah, so I'm using the right mouse button, and right mouse button clicked and going from left to right, from up to down. Okay. Yeah, this is also a Windows machine here on this Mac. So it's should be not. So is this auto view all? Is this on? Okay. Alex, shall we use the lookup table?
Maybe it's also a graphic card. But no, if you kick mine auf den Output von dem Bild, das ist the Output Inspector. On the right side, this Output Inspector, you have this 3D tab. This at least works on this computer.
So I'm here. So I'm here on the right side. Yeah, so here and here on 3D. So maybe so what happens if you're pressing here in the panel of the View 3D LOT for lookup table? Does this change anything if you're changing here? Or giving this one here, this white spot, try? Okay. Okay. Good. So, but these all are orange modules. So I will, we will check it out later. But the modules could also have a different color. And I will show you what colors we have here and explain the type of the modules. Yeah, so we can have blue, green, and orange or brown, or I don't know. So, and those blue ones, these are full of algorithms. Yeah, so algorithms which are implemented in C++. These green ones, and you also see it at the half circle connector, so this is a visualization method behind that. Yeah, so green ones you can use to visualize something. And the blue ones are algorithmic ones. And those orange ones, they are very interesting because they encapsulate algorithms in them. So this you can do. On the View 2D, just give it a right click and show internal network. So, and what you can see is that a lot of modules are encapsulated in this orange hull. Yeah, so, and encapsulated are green modules, and also I would like to step in here, for example, and there are another green ones, and another green ones, and here, for example, we have again blue ones. Yeah, so the orange modules that encapsulate whole networks. Yeah, so we are calling those rectangles, we are calling modules, and if we have connected modules, we are calling that network. Yeah, and the data flow is always from bottom to top. I think this is sufficient as a basic introduction. Alex?
Yeah, I just saw here that these max will have intergraphic ports, and we would have to set some environment variable, but we will try to do it without this 3D rendering.
Okay. So, yeah, what we encountered now is, or what we have learned is that you need a graphics card.
Yeah, I mean, as yeah, I turned it on. So for those who want to try that and know how to do it, you could set an environment variable, but I guess we will do it for now, and you just remember what we did and do it on your home PC. Okay, so now you're all experts with MEVIS Lab, and we want to build an application. So on your desktop, you should have a folder called Workshop. Please locate that. And in there, you should have 3 folders. One is called Clinical Application, and the other is called SciArt. These are the 2 we will use today. And we will start with the clinical application. Does everyone see that? Okay. So, yeah, after this workshop, we will together, yeah, we will give you some instruction where to get this demo data. Now, Sabrina should have a USB stick with the data. So I will wait for a couple of seconds, but the other who already have that, what they can do is yeah, clear out the MEVIS Lab, so you can close this document by pressing the Close tab. Then you should see this. And then just create a new document with this icon. So we have a clean and fresh environment. Create here. Or File New, or Control N, couple of ways. Okay, so does everyone have the clinical application folder open now? Okay. Yeah, so I'd say rather stop me if you can't follow than me asking every time if you have it. Yeah. So please just interrupt. If, and I suppose that this might happen due to the time, and it's always rather complex than we think beforehand, we prepared the finished version for you so that you at least can use the final application if you can't follow what we are doing interactively. So in your folder, you have, on the one hand, the My Brain Surgery Support MLab file, which is from which we are going to start building an application. And the Brain Surgery MLab and the other files, the Python and the script file, which we will cover, they contain the complete final application. Yeah, so if you just want to have a look and check out the final application, you can drag and drop the MLab into MEVIS Lab, or also just double-click it. It should open MEVIS Lab. So you should see something like this. Hopefully, on one PC, I saw a red module. If you have a red module, this means I made a mistake and it's not part of the public version. So is this the case, Sabrina? You have a red module? One? Okay, how is it called? I guess you can always zoom in by scrolling in the network using 2 fingers on your touchpad. Brush editor, okay, no problem, great. Then you will have to do more work. No, I wanted to use this to segment a tumor, but luckily we already have a segmented tumor image, so we will rather use that, because I guess with doing the fiber tracking, we will have enough to do. So I will close this again. You can leave it open. No, I will leave it open. We can always switch there to check, to have this reference for our final application. I will now create another document and load this My Brain Surgery Support MLab. And there we also have a couple of modules. You should again have one red module. Just click on it and press delete. On Macintosh laptops, you might have to press the function backspace together. So the FN is in the lower left and the backspace is in the upper right of your keyboard to delete stuff, or just push it aside. So we will start with this. And what I did here, you see the couple of modules, and they all have a different purpose, of course, and I already loaded them, so you can conveniently use them, and we won't need more than these modules, okay? Of course, there are a lot more in the database, but we won't need more. These are all the modules we use today. And also at the bottom, you see 4 load image modules. Please press the triangle to inspect the data being loaded by that module. On the left-hand side, we should have the brain mask. Let me zoom in a bit. So these are important now. So here we have the brain mask. Yeah? You should see something like this. So it's just a binary image which delineates the brain from the head. To understand that, you can, let's first or second inspect the T1 pre. Click on the triangle, and there you should see the MR image of our patient. And you can see he has a very nasty glioblastoma. That's a big tumor inside its head. So you can see here that clearly the brain, but also, of course, the skull. but for our purposes, we are not interested in the skull, so we already delivered or gave you this brain mask. Yeah? And we will later use the brain mask to separate the skull from the brain. And we also have this tumor mask. If you click on that triangle, you should see a blob like this, also a binary image, which delineates this big tumor you've seen in the T1. T1 is just a name for a special MR sequence. And then the most important thing today, maybe you have seen this poking Florian, this brain over there. If not, after the workshop, you can have a look. This also explains what this DTI and fiber tracking means. So if we click on that, DTI vector, we should have something like this. Or you should have a very bright white image now. Because what I'm doing here, you can see this contrast brightness icon. This can be done by right-clicking and moving, but with a touchpad, it doesn't work. So if you have a mouse, yeah, I'd advise to use that. Here is one. So I don't know. But we can also change the contrast and brightness later using a different way. So everyone is able to see these images. If not, raise your hand. Otherwise, I will proceed. OK? You don't see? What don't you see? This one. So if you click on the triangle, nothing appears. On the wrong triangle. Okay. Okay, because you have to note that these modules already have, if you double-click a module, you always get the user interface of the module that someone has written. And there you can see that a data path is given. So this module is able to load. You can see the status, file open, so everything's fine. And yeah, this is the case for these four, just for your interest. If we go back to the folder, you will see this data folder, and there these four images are. You don't see this panel. If you don't see this panel, what you can do, you can go to panels. No, you don't. No, what I do most of the time is here. On this bar, this gray bar here with the icons, go to the place where there are no icons and right-click. And then you get all the available panels of the MEVIS Lab IDE. And there you should then select Output Inspector. So you can see that it has a check mark. If I close it here accidentally, I right-click here and go to Output Inspector, and it's there. Okay. So what do we want to do? I want to write an application for clinicians to plan brain surgeries by being able to inspect important fiber tracks. These are basically neuron connections which go through the brain. So let me just pull this up. You can see here that the tissue inside the brain is lighter than the tissue on the cortex. This is due to that on the cortex you have a lot of neurons that do all the work in your brain, and they are connected via axons. So each cell has a long axon which transmits signals if fired, and they all go in bundles through this white matter, so-called white matter. And what we will do, we will make these fiber tracks visible. Yeah, and this is important for surgery because you can imagine if such a tumor grows, he pushes important fiber tracks aside, and for the surgery you want to know where it has pushed important fiber tracks too, so that you can do your incisions correctly without harming
important functions like speech or movement. So this is the aim. So what we need to do is we need a method to be able to do this fiber tracking by adding seed regions of interest. So telling an algorithm where it should start tracking these fibers. And we want then to display this in 3D or in 2D. I suppose we would have to do this in 2D mostly. But let's see how far we come with your intergraphic boards. Otherwise, I'm sorry then, but you at least can see how it looks like on my computer. So let's start. So first of all, we need these 4 images. I've just selected all of these, and then click on one of these to move them to the right. So we have a little space to build our network atop. The first thing I want to do is using this tensor tractography module. What this does is that it takes in an image on this connection. So click it and connect it to your T1. Oh no, sorry, to the DTI vector. To the DTI vector. How to remove what? Yeah, you can, if you want to remove a connection, click on the connector, draw it somewhere else, and release. This is one possibility. Or you can right-click the connection and say disconnect. So you see it gets highlighted, right-click, disconnect. Okay. So for this tensor tractography, we need a so-called seed region of interest, some seed points, some points from where the algorithm tries to track the fibers, and to make visible to you why this works, grab the vector to color module and also connect it to the DTI vector module. And then click on the output, and you should see something like this. Yeah, so what this does is it takes an image which at each pixel or each voxel has a vector, so a 3-dimensional arrow, and turns it into color. So X, Y, Z components get converted to RGB, basically. And then you should see something like this. And what does the color mean? Red means the main direction of the vector is from left to right. Green means the main direction is from front to back. And blue means the main direction is from bottom to top. Just click on the output connector of vector to color. Yeah? So it's always the bottom is the input, the top is the output, what the module has computed. Okay, so that's the first thing. And you have to understand that this DTI vector image is a volume where at each voxel you have a vector pointing in some direction, okay? That's easy. And if we now put some point, some virtual point inside this volume, we can track it through this vector field. So we assume that the vector field somehow takes the particle and moves it in its direction where it points to. Okay? So you can take a point, make a time step, carry it into the direction where the vector points, and then we will get to another vector in another voxel if the point has moved far enough, and then it changes basically its direction, flowing through this vector field. So you can trace a particle, a virtual particle, through this vector volume and basically create a track, a fiber. And we will do that now, so we have to create a possibility to draw these C-drawings. So first of all, we need a viewer. Let's take the top or to view 2D. Or to view 2D from the top. And connect the T1 to the auto view. You can then double-click the auto view to get something like this, the interface of this module. You can left-click in any image to set the cursor and jump in the other directions. Or you can also hold down the left mouse button and move it around to move the cursor. Okay? So this is the first thing. Now we want to add a possibility to draw regions of interest, similar to what Sabrina showed you with this manual segmentation. Yeah, we want to be able to draw a circle or any other kind of two-dimensional form. So let's close this again for now. And to draw such things, we have a library called CSO for contour segmentation objects inside MEVIS Lab. You see a couple of modules here which carry this abbreviation in its name, like CSO convert to image, list container, visualization settings. This brush editor I will delete because it doesn't work on your installation, but the spline editor works. So we have now to connect a couple of these modules to be able to draw CSOs. By the way, you can always right-click a module, get this context menu, and in the help menu, you can open an example network if it's there, but for the public version, each module should have an example network. So you can click it, another document opens with a small example network, some explanation on how to use it. But I will show you now how to do this manually. Of course, you could then copy and paste it in your network. But now let's start this process. So first of all, we need this spline editor, this CSO list container, which basically stores the thing we have drawn. And then we need a ZoView2D extensible editor. ZoView2D extensible editor. This is most important. This has the logic on grabbing mouse input and turning it into CSOs. And then we want to connect this output to the middle half circle input of the ortho view.
By the way, each of the modules also has a help page. And not only an example network, but also a help page. And so if someone does not know how to use it, then help is also there. That's just mentioned.
Exactly.
So you don't have to know everything about those modules. Yeah? So it's just that Alex now explains how to use them and stuff like that, but it's also in the help and in the example network.
Yeah, thanks. Okay, we're nearly done. Now this ZoView2D extensible editor needs a place to store the drawn CSOs. So now we connect these two. You see it's only possible to connect it on the first connector. And then the extensible editor is extensible because it doesn't implement any specific method on how to create contours. And this is done by these extensions. And ZoCSO Spline Editor is one of these extensions which implements a concrete way to draw contours. So we connect these half circle things together and tell the extensible editor that it should use the spline editor to create contours. We now should be able to double-click the ortho view again to open it, and you should immediately see that my icon has changed and has this small wiggle next to the cross. So I could now start drawing something like this. Yes, sure. Okay. Yeah, we would have to change one thing because you have drawn this thing here, right? And it really places a point every time you move a mouse, but we want to rather have a more organic shape. So we can parameterize the spline editor. I will do it again. Double-click the CSO spline editor to pull up its user interface, which allows to change parameters. And you should still have tagged these use freehand mode checkbox. Just check it off. And if you hover a little, you get this tooltip. If checked, the CSO is generated only while dragging the mouse and is finished on releasing. But we don't want to have this. So if you've already drawn a CSO, you can clear everything by pushing this small clear button on the CSO list container. Yeah. And then you can start anew. So make sure that when you're placing these points, you are close enough to the starting point, click, and then it gets closed automatically. So that's easy. We now can draw contours with just a couple of modules. And now we want to turn them into fibers. I do. You have a question? How you show, you can always double-click, you mean this? Double-click a module to pull up its user interface. This one? This one is the user interface of this author view. Do you mean that? Yeah. Here you can see the panel author view 2D. It gives you the name of the module. So you can figure that out by looking at the title of the window. And of course, you are free to change the layout here, to play around with it, make a cube layout, whatever. Row equal is good for this use case. Sorry. Okay, so we can draw splines. Now we need to turn these splines into markers that are simple points on a plane that we can feed into the tensor tractography rightmost input. You can see if I hover over there, you see it says allowed as an X marker list. This is another specific data structure which contains just a list of points. So we need to get points out of our contours. For this to work, we need, let me take a look, convert to image module, CSO convert to image. It does a bit more than the name suggests. It does not only convert a CSO to an image, but also can give you output X marker list. You can see here on the second. So the CSO convert to image, to be able to convert a contour to an image, so basically a binary mask, for example, you need a reference grid. Yeah? You need to know, or the algorithm needs to know what resolution does the image want to have. And you can provide a reference grid by connecting our T1 to this image input. So now the CSO convert to image takes the properties, the dimensional properties of the T1 image while converting the CSO into image space. And if we take a look, here you can see that this image has a resolution in X of 172 pixels, in Y of 455 pixels, and in Z it has 473 pixels. Okay, so this is our grid now. And then we also need, of course, the CSO. It should convert to images, right? So we connect it to our container, which contains our CSOs. And then let's double-click on the CSO convert to image to see what we can do with it. Basically, here you could set the value of the foreground, so every pixel that is within the spline, that's the gray value it should get, and the background. So right now, or most important at the bottom, you see the progress bar, and you see the update mode. And currently, it does auto update. So anytime the input changes, it does an update. So now it states it already has computed something. The progress bar is at 100%. Let's check out how the image looks like by clicking on this output, and make sure here you can take a look on which slice you have drawn your splines. If you haven't any spline right now, draw one by just clicking here. And then I see here on slice 291, in my case, I have my splines. So I will want to scroll to that slice to see the voxelized contours. Yeah. And now if I hover over the bright area, you can see in the top left corner of this output inspector here, the gray value. Here it's 0, here it's 4095. Exactly what has been specified in these two boxes. So it works, that's important, but we don't need the image, we need the X marker list. So if you click on the second output, the output X marker list, you should get in the output inspector something like this. Here you have the number of markers that have been generated. And there you should be able to click on the 3D tab. Do not click on the list tab, because it would take, if you have a lot of markers, quite some time to populate this list. So you can click on the 3D tab, and then if we zoom in, which is done by pressing Control, yeah, how to do it on a touchpad. You can use 2 fingers on the touchpad and just zoom. The same, should be the same. But you see the markers, right? That's most important. I just wanted to show you, if I zoom in, that you see individual spots, right? And they really are aligned to the image grid we have passed into this convert to image module. Okay. So now we got our X marker ready to be fed into the tensor tractography. So let me rearrange this a little to keep the network clean, and connect the output to the tensor tractography input. And it might take some time if you already have added some splines, because the module then really does something and computes stuff. And if you, options. If you click on the output of the tensor tractography, on the output inspector, you should be able then to see something like this. If you don't see anything, go to the options and press View All. Yeah? The extensible. Okay. So, are there some who could draw CSOs? Okay, but basically you are able to create splines, but they can't. Okay, let me have a quick look. Oh. So we have the container, spline editor, allow creation. What we can try is open the example and see if it works there. Okay. So it's not a basic problem. If we open the example of the spline editor, it also works. So what I will do, I will copy this. Delete that. Paste it. Use that. Put that back there. And then we are ready. Okay. Okay. Just for you to know what we did to fix the problem, maybe it might be that some setting has been changed, some default setting. What we did, I right-clicked on the CSO spline editor, went to the example network, checked if everything works, and it did. So I just copied the important modules, these 4, pressing Control-C, as you are used to it with other programs. Close the network, go back there, press Control-V to paste it where the mouse is. And then you are ready to use that part of the network. Okay, so now we have the problem with the tensor tractography. What I want to do right now is I delete all my C-drawings again and just draw a simple small one, maybe somewhere here. Okay. And then the tensor tractography should immediately do something. So does it still not work? I mean, what we could also do, let's maybe take it one step further and use the SO fiber width, for visualization. SO is, by the way, for scene object, just if you wonder. And connect the fiber output to the SO fiber width input. And if you then click on the half circle output of the SO fiber width, you should get the access to the visualization scene. So basically, to explain what all this does again, I've explained the CSO part here and the CSO convert to image. but the tensor tractography, what it does was it takes this vector field, takes a bunch of points which lie in the vector field, and then does starting this tracking. Yeah, you can see here for the tracking you can set some stopping criteria, like check for the curvature. If the curvature is too high, it stops. If the anisotropy is too high, it stops. You could play around with these settings to see what it does. But the module I've put into my brain surgery support basically does yeah. You also can't draw. Okay, let's do the same. Go to help, show example network, take this bunch of modules, control copy. Let's delete that. Delete that. Delete the container. Control paste. Put it there. Put it there. There we go. So for the ones that are ready, you could just play around a little with these parameters, for example, or with the parameters of the so fibrous.
How do you bring up those little rotary controls?
These ones, they automatically come when you use this output. They don't. Then maybe let's try to pull over this So Examiner Viewer module and connect it.
Just down below there is the options part, and from the options part,
Ah, yeah.
you can use the decoration. Decoration enables you.
Yeah. And if you click this icon is very important. It always centers the scene. So everything that's in the scene gets centered so you see everything. This dotted box around the two geometric objects. Okay. Should I proceed? Sabrina? So maybe I can just talk a little bit about the modules for the ones who are ready.
The So fiber width is green, or maybe in general talk about the green color of the modules. They are responsible for visualization. They use OpenGL for rendering, for those of you who are into it. And on top of that, we use OpenInventor, which is a scene graph library, scene graph-based visualization library, which allows to build up complex scenes and prepare them for rendering. And you would be programming these in C++. You can, of course. Yes. True. Yes. Yes. Basically, we have here the help, which has extensive explanation on all topics. I would go there. Or it's always good to learn also to take modules that are already there and inspect how they work. For the Python-based modules, I have to add a note. So the blue ones are written in C++ always, always. You could go there, I guess, and say run project wizard. I don't know if the public version has it. And here I could say I want to write a new ML module, and it creates some scaffolding. Yeah, you on Windows, you download the public version for a specific version of Visual Studio, so it is compatible. Then you need that specific version to compile. And on Mac and Linux, it's similar. So yeah, it's similar there. So on Mac, you just have Xcode, and on Linux, a specific version of GCC. Yes. No. Xcode. And for the Python-based modules, you'd create macro modules, because macro modules are basically, they have no DLL behind them, but rather another network. But you can have a macro module without a network. What this really means and how to program that, this will be the last step of this clinical application. You will get an introduction, and there we extensively use Python and also for writing business logic of applications, but not really for high performance tasks, of course. Okay, so in the meantime, what I did, I connected the So Examiner viewer with the So FiberVis. And if you then double-click the So Examiner viewer, you get this 3D viewer and can left-click and rotate to inspect your beautiful fiber set. Okay, so we are nearly done. We can now track fibers, and we want to use that to see how they are pushed in relation to the tumor. Okay. If we go back to the T1 pre and scroll a little, just to remind you, we have our tumor here, and we could now go into the details and pull out modules to segment the tumor, but I made it easy for you, and you should have this local image called brain mask. Sorry, tumor mask, of course, tumor mask. So we will use this. It's already segmented. Now we just want to display this in 3D, this mask. We've learned that the volume rendering does not work on your systems, so we will render simple meshes. In order to do that, we would need to, I can at least show you here how it looks like in 3D. So this is a volume rendering of this binary image. And now I want to create a mesh around its surface. Yeah? This process is called iso surface creation.
So let me see if, yeah, we have it right here in our small database, ISO surface. ISO because I expect you know the landlines on maps where you can see the altitude of a mountain, and yeah, you have these circles around, and this is a certain ISO value, ISO being the same, meaning the same. So what we want to do is connect the tumor mass to the ISO surface, and then double-click the ISO surface and select our ISO value. How do we know what this should be, you might ask. So let's get back to our 2D view in the output inspector to inspect the value of the mask. Yeah, so click on the triangle, scroll to a slice where you can see the mask, and if you hover with the mouse, you can see here in this corner the gray value. It's 255. Yeah? So you can imagine that around this edge, by linear interpolation, of course, we have all the values between 0 and 255. Some 255 is very near the edge of the mask, and 0 is a little bit further with respect to sub-voxel resolution. So it doesn't really matter if we take 100 or 200, but anything below 255, so the default should be fine. The resolution here, 1 is just the highest possible, meaning he really inspects each slice of the image. So we are really just ready to hit apply. You should see your progress bar getting complete, and then you should be able to, let's directly connect it to the examiner viewer. Let me pull these over. Because they belong to the 3D viewing part. This is our 3D viewing, this is our 2D viewing, and I connected to the examiner viewer. Now, you might wonder in which order. This scene graph that is built up by the screen modules always traverses a graph from the root node, the topmost node, to its children by left to right. So everything that's more left is rendered first. Yeah? Basically, it's not that important since we have a Z buffer in graphics rendering, but at least for transparent objects and stuff like that, it's important. So it shouldn't make a difference here. If I now double-click, you can nicely see our fiber tracks next to the surface tumor rendering. Okay? But we want to be able to change the visualization a bit of the mesh. We don't want to have this gray bulb, but rather change its appearance. So we need a specific module to be able to change the visualization. And I see it's not in the database on the left. So what you should do right now is click into the search modules, or just click on a gray spot in your network. And if you start typing something, you see the focus is automatically in the search box. And you can type in letters and see what kind of modules pop up. So I start with SOWEM. And then you get the ZOWEM renderer. Okay, ZOWEM renderer. WEM is short for winged edge mesh. It's a specific structure on how to store triangles. So how you just use your arrows on the keyboard to go through this list and hover over the ZOWEM renderer and hit enter. And then the module gets instantiated below your mouse pointer. Pull it over to the ISO surface module and connect the right output to the left input of the WEM renderer. the only one possible. So what's the difference here? The right one, again, transports an arbitrary C++ data structure, which in this case is a VEM, so an array of triangles. We don't need this connection anymore, so just pull the strip and release. We rather connect the VEM renderer now. It gives us more control. You don't have to do this right now. I just want to show it to you. I can dive into this macro module, show internal network, and there you again see a VEM renderer. So basically it uses the same method to render, but it does not expose all the settings that the VEM renderer has to its outer public interface. This is just a design decision of the creator of the module. But we are still free to provide our own VEM renderer, pull up the 3D view, double-click the VEM renderer, and here we get a bunch of options to change color, for example. So here I want to take some yellow. You can use whatever you want. I double-click the renderer to get this panel. And change the diffuse color to maybe a bright yellow or whatever you like. I'm going for this, and we're okay with that. Okay. Looks good. We are nearly done. Let's take a look on what kind of modules are left. So we can't use this GVR overlay due to your Intel graphic cards. It's not that important. It would have allowed us to overlay the color map onto the ortho view. This so view to be seen could work. Let's take this. So view to be seen. Pull it under your ortho view and connect the so fiber with. So what this basically does, you can read it from the name, so view 2D, meaning it's an extension to the 2D viewer, which basically is also inside the ortho view. And it will render a scene on a slice, a 3D scene on a slice. So basically you can put any 3D scene into this so view 2D scene, and it tries to render it on a slice. And it knows which slice to render on because it's an extension to the so view 2D module, which has the knowledge on what slice to render. I want to connect it also to the second input, but this is already used by our extensible editor. If I would connect it, I would lose the connection of the extensible editor. So what can we do? We take a group module, which basically just allows us to have multiple inputs and one output. So grab it over, or as you have learned, just type in so group, hit enter, you have another one. By the way, you can always click a module and press Ctrl D for duplicate. And then I can create a bunch of duplicates. I can press Ctrl Z to undo. Okay, so I have my zo group, and I want to connect the extensible editor to it and the so view 2D scene. And then connect that to the ortho view. So now we have connected both. If I then open the ortho view, you should be able to see your fibers rendered on the slice. Let me zoom in a bit. Here. Change the contrast. There you can see them, right? So it's now a cut through our three-dimensional fiber object. Okay. Yep. By the way, to not lose your work, you can just save by pressing the Save button. If you change something, you get this star next to the name, so you see the network is not stored. Control S also stores. So it basically, MEVIS Lab does the same. It tries to expect you, or fit your expectations with respect to shortcuts. Okay. So we have our ortho view. We are able to draw fibers. I get a new fiber. I have my 3D view with my tumor and fibers. Looking nice. So we have a bunch of modules left on the left-hand side, but they are basically there for doing the segmentation of the tumor ourselves, which you don't want to do with the slice interpolation, for example. So don't get confused that we don't use them right now. But we will use this so toggle. Let's use that so toggle, toggling like a switch, so you can activate and deactivate a specific subgraph of your rendering. Okay? So let's suppose the clinician has the feature request that he does not always want to see the fibers in the 2D view because it obscures the MR image behind it. Okay? So there's a use case where he wants to see it, but also he doesn't, or she. So what we can do, we can just integrate a simple toggle in between. You now, what we haven't done so far is you are able to drag and drop this module onto this connection. It highlights. You can see that it highlights. And then release, and it gets just put in between. But of course, you can do it the conventional way by dragging and dropping yourself. I can double-click this so toggle. It has a very simple user interface, just a checkbox. And you've probably seen also a checkbox here on the green, which for some modules has been implemented to have fast access to common functions. Because for things like a toggle, as a developer, you don't always want to open this simple user interface, have another window to click this on and off. You'd rather want to have this fast access so we can use it also. It's basically the same. It's the same as the checkbox here. And you might already have seen it. If I click the toggle now, the fibers are getting invisible because this subpath does not get executed. The so toggle is set to false, so everything below that does not contribute to the rendering. So we basically have set up the tool to be able to switch the fiber rendering on and off. But now, our clinician, of course, cannot work with this method of a network. he or she wants a nice normal application with a normal window, as you know, as everyone knows. So now we can do that with MEVIS Lab. We can write a user interface with some logic on it, and the end user does not see this network that we've built. It's just a means for the developer to create a complex application or complex algorithms or movies. So now let's start putting our parts we have, like the 2D viewer, the 3D viewer, the toggle, into an application. To start with that, you have to press Control E, which opens up the editor called Mate. MEVIS Lab Text Editor. Control, maybe on a Mac you would have, if you are on Mac OS, you would have to press Command E, but on Windows, press Control E. But you can always also go to Show Mate, for example, or here, scripting, edit network script. Here you can also see the shortcut. Control E for edit. And on Mac, you should see Command E there. OK, so let's do that. And it says you should write your script there. So let's start. It has created a mybrainsurgery.script file. The network we have is a .mlab file for MEVIS Lab. And this is now a .script because it contains the domain-specific language of MEVIS Lab called MDL for MEVIS Lab, or MEVIS Description Language. Its syntax is kind of similar to JSON, and yeah, allows you to describe the user interface of your network, yeah? And to listen to events that happen, for example, clicking on a button. Then you want to execute a certain script and do something. So let's start. We can delete the first line and want to start by implementing our window. So we just type window. And you have full auto-completion in this editor. And the editor knows about the MEVIS Lab network behind it. So you will later see we also have auto-completion with respect to our modules, from which we pull user interfaces into our user interface. So I say window. You can give it a name, but don't have to, because you can define multiple windows, but we don't want to do that right now. And we will have, let's start with how big the window should be, okay? So you say width. You can, if you start typing and you've done something wrong, you can delete, and you can press Control Space to get back the auto-completion. So width, let's say 1,000 pixels. And the height should also be 1,000 pixels. OK. Let's see what happens. Let's see what does it look like. Just save it, Control S, so that you don't have a star. Here you see if I type, I get the star to make sure it's stored. Press Control S. Then you can use Alt-Tab to go back to MEVIS Lab, or however you switch between applications, what you're most comfortable with, because the mate is a separate process. And what we now can do is we can execute the script. Yeah? We can press Control R for run. Like here in scripting, start network script, Control R. And we have a window with a size 1,000 by 1,000. You can see it might be a little bit too high. So in my case, I would change it to 800. can do whatever you want. And what I did, I clicked into the gray network, somewhere in the network on the gray field so that the network is in focus, press Ctrl R and it just immediately reloads. Reinterprets the script file, dynamically builds up the user interface and opens this window. But you see no content specified. We haven't added anything to this window yet. Let's do this now. So first of all, we don't want to rewrite everything, and our modules already have user interfaces, like this Ortho2D view. Why not reuse it? Yeah? So let's reuse this Ortho View 2D user interface. We go back to our script file and start off with a category. It's not so important. It basically helps you setting up multiple tabs in your application if you wanted to. And it is kind of a container for all the user interface elements we will want to add. Give it a random name. Again, main, for example, doesn't matter. We opened up a new component, and now we start to really add interesting stuff. So we want to reference an existing user interface. For that, we have the panel command, because we want to reuse a panel. Then you can say inside the panel we can parameterize it, and we want to reference a module. So start typing mo, and this module should come up. And there, what do we see? We get a list of all the modules in our network. Isn't that neat? So you can start typing. So it was called Ortho. Are you sure that you have proper curly braces? That you are in the correct context? The first, okay, maybe that's true. That it does not give you the first. Maybe that's also difference between the Mac and Windows, I don't know. But you can just start typing, and of course you can always go back to your network and just take a look. So Ortho View 2D, save it, and let's go back and see what's happening. Pressing inside the network, Control R, and there we go. So the first half is done. On the lower part now, I would like to have the 3D view, okay? The 3D view. So what should I do? Any ideas? So we want to reference the SO-Examiner viewer. We could do the same thing with the panel, but for specific viewers, only 3D viewers, there's another type, UI type called viewer. And there you reference the SO-Examiner viewer. And some cryptic self, I won't explain it here right now. It's basically self-reference to its output. Yeah. Let's see what happens. Okay. What I don't like, of course, is that I have this empty space here. So we would have to set the expand settings, how the user interface should behave when resizing the window. So in the category main, type expand Y and set it to true or 1. I always use 1. And there you go. So now so it now equally distributes the available space to its children, and the children are the panel and the viewer. So both get 50% of the available height. Okay. I said that we wanted to allow the clinician to turn the fiber rendering in 2D on and off. So let's add a checkbox in a new settings panel that allows to change some settings of the visualization. Okay, so I'd like to have it on the left side. It's a panel on the left hand. So what do we have to do? First of all, you saw that the category automatically distributes its children in vertical order. Yeah? But now I'd need my panel on the left-hand side, and then everything I have right now on the right-hand side, so this is horizontally aligned, all that stuff. So let's take this horizontal layout command. Just above the panel, horizontal. So everything's in there is layouted horizontally. And yeah, let's put a box here, box. Let's call it settings. And now I want to reference a field from this so toggle, this checkbox we already clicked. So I type checkbox and reference my so toggle. Start typing so toggle. We only have one. And the dot notation allows me to now pick a specific field. Yeah, field are the fields are the arguments to the module, so the public interface of the module. And the toggle, the checkbox on the so toggle is called on. The field is called on. It's true when it's on and false when it's off. So let's reference that. So now what the user interface creation process does, it creates a checkbox, and this user interface checkbox element controls the field so toggle one on. So in MEVIS Lab you have a nice separation between user interface and logic. We can verify this. You can right click on so toggle, go over show window, and don't display the panel but the automatic panel. The automatic panel is always created by MEVIS Lab. If some colleague was lazy and he or she did not wrote a nice panel, you at least always get this, a list of all the parameters. Yeah? And here we can see, okay, on is this bool thing, which is now set to true. You can also change the value here, but that's the correct field. Okay. So let's see what happens after we have added this checkbox. Okay, so now we have the settings box with this on, and below that, but yeah, below the viewers, but I don't want them to be below, but rather on the right-hand side. So let's fix that. Everything we put in here is horizontally aligned. And what we want to have, I want to have the box, and then we want to have next to that the panel with the viewer being vertically aligned. So let's put a vertical in here, and then just cut and paste. So you can use your mouse to make a selection, or you can go to the first line with your cursor, press Shift, and then the arrow key downwards to select lines at once. Arrow up and down by holding Shift. Pressing Ctrl X to cut. Going up, pressing Ctrl V to paste. Of course, you can also just rewrite everything. And we are done. Let's get back. Ctrl E. And yeah, we are nearly done, but we forget to set the expand settings. So, first of all, the horizontal stuff should also expand on Y. The box should have a fixed width of, let's say, 150 pixels. And the vertical thing should also expand in Y. So we've set the expand Y in horizontal, the width in the settings box, that it's not so taken up half the space, and the expand Y in the vertical for our two viewers. Let's go back. And that didn't work. Y width 150 box. I saved it. Okay. Yeah, width. Okay. I should have set the maximum width. You can also set the maximum width to 150. There are different ways to lay this out. Or I can say, please, layout manager, do not expand this box in X direction and horizontal direction. So I set the expand X to 0. I guess we don't need this. And then it does respect the width. Okay. So I'd say we now have a very basic clinical application to do fiber tracking and check out the relation of the fibers to the tumor. Yeah, we could now add more stuff to the settings, like deleting the contours we've already drawn. This should be straightforward now for you, since you know we have this clear button here, which also is in the field list of the automatic panel. I can also click it here and everything gets deleted, and we could, similar to the toggle, push this into the user interface, pull this into the user interface, and would have this functionality of deleting contours in the front end. But I will leave it by now because we want to also get to the second step. The final application that you will see if you open up the brain surgery MLab is a bit different. I added a bit more settings here and there, but basically this is what I wanted to do with you. So I hope you could follow that. Are there any questions with respect to that? You want to know? Has everyone gotten that far? Okay, you did? Huh? Okay, okay. Okay, so that's that application. And this is the process all of our colleagues are really doing on a day-to-day basis at MEVIS, using this platform to develop new algorithms, talk to clinicians, being able to prototype and change on the fly. And now I want to give you my idea on how we could play with this fiber stuff a bit more artistically, yeah, but it's really just a starting point. So let me start by loading the SciArt Twitter Brain application. And if you want, back home, we will provide this for download later on and distribute this. It's the same process. Yeah, you can use the My SciArt Twitter Brain to build the network up on your own if you want to, but I guess due to time, I will now show you what I did there and what my ideas was, and play a little bit with that. So you might know that in brain science, I'm here on the brainmadesimple.com page, that your both brain hemispheres have different functions. They are there for different functions, right? So we have the left brain, which ought to be being more logic for language processing, reasoning, science and math and stuff, analytic thought basically, and controls your right hand and your right body. And the right brain function is for art awareness, creativity, and stuff like that. And since we are here under the umbrella of sci-art, let's use this. And my idea was, let's take a Twitter stream and check out for hashtags that have art or science. Yeah? So we want to have hashtags. We search for hashtags with art in it and hashtags for science. And every time we get a tweet, I would want to somehow visualize that using the left or the right hemisphere and some fibers I've created on the left and the right hemisphere. Since I don't have the best internet connection right now, and the Twitter API also takes some time to download tweets. I've already downloaded some tweets yesterday, and you will also get them. They are here in the data, tweets and tweets2 JSON. Like, I guess 200 tweets are in there, and I searched for hashtag art and hashtag science in them. And basically, this is a quite big of a network. So basically, I'm doing the same. I have also such a DTI image, which allows me to track fibers. I have my MR image, T1, and I have a couple of modules. I will quickly go over this, that you roughly understand what I'm doing here. So first of all, again, I need to draw my contours to be able to track fibers. It has to load the data right now into memory. And I said I wanted to use the left and right hemisphere. So let's see. You can see here's a big R. This is for right. So this is the right-hand side. This is our right brain. And if we go back and see, OK, right was for art. So I want to start here with the, let me see how we can do this later. I will just draw two rows and one in the other half. And then I also, in this demonstration, use the connection between the two brains, the corpus callosum here. I would use a small part. I wanted to use this and search for hashtags that have sci-art or art-sci for the connection of these two. But the tweets I've downloaded don't contain any, I think. But anyway, I draw this. And now I should have 3 different fiber sets. I will open my viewer, and here you can see 3 different fiber sets. Yes, this examiner window with the 3 so fiber width things. Exactly. Yeah, so here you can nicely see the corpus callosum, which connects your 2 brain hemispheres together. So a lot of traffic goes over there, and this is the only connection your 2 hemispheres have. And interesting personalization changes happen if you don't have this connection. And here we have our 2 strands of fibers for the left and right hemisphere. Okay, now what did I do? First of all, I want to control each fiber set separately. Yeah, so all these networks here are a copy of each other. They are basically the same. This one, and this one. So if I haven't been too lazy, I could have put them into a macro module to not duplicate everything. And what it does is, here, you know, this tensor structure free, and below here we have a filter, CSO filter. Since you remember I have drawn 3 CSOs, you can see them in the CSO manager here, 1, 2, 3. And the filters are used to separately use them and filter out. So the first filters includes only the first CSO, the second CSO, and the third. So I have these all separately laid out here. Yeah, and then I use them to track the fibers. And now I have a marker list filter, so I'm rendering this stuff also by converting the fiber to little dots. If I zoom in, you can see these are all little dots now, and no consecutive lines anymore. I did this because I wanted to be able to filter them, to only show a subpart of them. So let's say I want to filter and only have 300 points left. And then you see I render a lot less. And I want to use that to react to the Twitter stream. And every time I get art, a hashtag, I will fully show the right-hand side fiber tract. Every time I get a science, I will fully show the left-hand side fiber tract. And over time, they again disappear. I render less and less points. So let me see if this works. I have written, again, a simple application like we did before. I have my rendering here. I used a simple brain rendering, some outline of this, and we see our 3 fibers here. And now I can start a stream. It's not a real-time Twitter stream, but rather using my already preloaded. Okay. It's again pressing Control-R. Yes, so clicking somewhere in the network and pressing Control-R. Yeah, I guess this is due to what you could do if you want to try this is disconnect this one here. This is the volume renderer, yeah, which has problem with your graphic cards maybe. So if I disconnect that and press Control-R, you see the brain is not rendered anymore. That should work for you. I will undo this. So here below on the right, the separator stuff here. Okay. So this one is noteworthy here, the tweet update. So this says every 2 seconds, get a new tweet. Okay. I will increase this to 5 seconds so we can take a closer look to this and then start the stream. So now you can see that the fibers are going away and I get a new tweet, but this tweet does not have art or science in it. But here, boom, I got a tweet that has somewhere contemporary art here, somewhere here, I don't know. Yeah, here, hashtag art, here, hashtag art. It's always art. Sometimes science comes up. Yeah, and hopefully we also get a blue line here. It's grabbing the tweets at random from my downloaded list. Let's come on, science, come. I will let it go a little, and yeah. So basically, here we go. There we go. Yeah, and I use some text rendering and place it randomly in the network to be able to read the tweet. And what could I mention else there? Yeah, the connection would also be nice. Yeah, having this third fiber tract. But of course, you can do this in real time by connecting to the Twitter API. You would have to create an app with Twitter, and then you have access to Twitter streams. It's a very simple API. There are Python libraries to do that. But what I saw is that a request to the Twitter API to fetch a new tweet sometimes takes some seconds, yeah. And since in MEVIS Lab, in this public version, we cannot have Python threads running it blocks the user interface. So I couldn't rotate that smoothly all the time. But basically, it should be possible. You could have two processes. One process fetches Twitter, puts them in a database or somewhere on hard disk, whatever, and MEVIS Lab, this process, grabs the tweet and does something with it, analyzes the hashtags. Okay, so this would be the idea for some exploration. Of course, you could then really dive into the network. What might be noteworthy here, what you've seen, this glowing of the stuff is this post-effect renderer. It takes a scene and does some glowing on it by applying a filter on the scene, and you can control the glowing effect, like, for example, here the intensity. Yeah, if I push it, let me, here, 5 or really no glowing, yeah. Or what I can do is the kernel size, some iterations, it changes. And what I did is every time a tweet comes in which has art or sci, I push this intensity to 4 or 5, and in each frame I reduce the intensity so it blurs out. And of course, you can animate any parameter you want to for such things. Yeah, I just took one parameter, this glowing, and the other parameter was this this filter list here, which goes down. So let me go back, start the stream, and then you should see here over time the maximum number of markers just goes down and down. So the fibers are vanishing. But that's, yeah, you have total freedom. You can animate any parameter you want to. Yeah, and just a small introspection, because you asked about Python, to give you this insight quickly, how we connect Python with this. So I need to execute something in a specific time interval. So for example, this glowing fading out, yeah? And for this, I have an idle trigger, which is set to 150 milliseconds. So every 150 milliseconds, this button gets pressed from the module inside, yeah? And I can now listen to this trigger output by the means of Python and the script file. So if I go back to the scripts file, we have written the window in our application, but what's very important also is this command section. And with the command section, you can supply a Python file. This resolves to the name of the network in the same directory, and add some field listeners. And here you see I'm listening to the idle trigger output. And I want MEVIS Lab to call the onIdle method I have defined in my Python script. So let's switch over to the Python script and locate that method onIdle. So this gets called every 150 milliseconds. What I'm doing here, it's quite simple. I'm looping over 3 numbers, X marker list. So if we go back, you see we have X marker list 0, X marker list filter 1, and X marker list 2. And the range function gives me a list of 0, 1, 2. And I'm just doing some string interpolation here to access the field of my X marker list, and then doing some gradual lowering of the value. The same for the post-glow intensity. Of course, you can play around with this diminishing factor and so on. And on next tweet is also important. So you can see we have another idle trigger tweet, which can be set in the user interface. Here, this one, 5 seconds here. And this calls on next tweet. And normally here you would then call out to the Twitter API. But what I did, I load the tweets to JSON. I load it into memory. It's encoded. I stored it at JSON. And I get nice Python dictionaries back here. And a list of tweets. And then I'm choosing a random tweet by getting a random integer between 0 and the length of the tweets, accessing my tweet array, getting the tags using this method, get tags, and then check, is art in the tags? Yes, it is. So let's pump up the num markers and the intensity. Is science in there? Yes, it is, and stuff like that. And here I calculate the position of the text and the text itself. So the tweet itself shows up here. Here you can see the tweet has a text field. And yeah, you can then do whatever you want with Python to implement logic. So I guess I filled up your brains now. And happy to answer some questions if you have, or close the session. Yes, sure. Maybe I can pull it over. Do we have an HDMI? Nee? Ah, back in hotel. So okay, so this brain is a colleague of mine called Florian. So we really put him into our MR scanner and 3D printed its real size. And then we put some LEDs into it. And inside the socket, we have an Arduino with a BLE, so Bluetooth connection. And then we've written an iPad app where you can see the rendering of the brain. And you might recognize this. We also use fiber tracking here. So what we wanted to convey is where on your cortex certain areas are and what functionality they have. And on this brain, we have a couple of sensors at the top mid where your motor sensor and motor areas are. So these, on the one hand, give you the sense of feeling if you kick with your foot against something and you feel the pain, but also if you want to control your movements. This is all happenings at the top of your brain here. And the further you go down, you go up in your body. So this parts here control your foot movement and leg movement, and on the side it goes up to your arm until it reaches your mouth, and so on. And now you can press the LEDs here, and if you look on the iPad while I'm doing that, you can see that the Bluetooth connection sends the selected LED index to the app, and the app displays another image. So these are all pre-rendered. These quality cannot be done in real time. So we have like 12 gigabytes of high-quality images in this application. And I can interact with this a little, look at different angles on it, also get the 2D data. And what we couldn't do is also display this color map on top of the MR image, which you might recognize from our trainings. And here below, for example, we have some explaining text. Right hand, these fiber tracks control the muscles of the right hand. And it's on the left hemisphere. Yeah, and we did this, basically, we have a big version, which is not mobile, which has really real-time rendering on it and a touch monitor where you can look at the brain really on all angles because it's rendered in real time. That has basically the same functionality. And then we thought it might be nice to have a smaller version, which we can bring around to talk to people about this DTI MR imaging method, which really is awesome if you think about it, because maybe some more detailed explanation, this DTI is an MR sequence which measures the movement of water molecules along the axons in the white matter. So you have the Brownian motion of atoms and molecules. They just randomly move. But in the white matter, they are constrained by the main directions of the fibers. Yeah? So this, of course, is a macroscopic effect. A voxel you are measuring has, like, let's say, at least 1 cubic millimeter. So a lot of fibers are in that cubic millimeter. So we don't directly measure single strands of axons, of course, but rather the movement of the molecules, which are constrained then by the fibers. And you do this by measuring the movement of the water molecules in different gradient directions. Yeah, so you take like 30 images of the brain and say, okay, how strong are the water molecules moving in that direction? And then you get a scalar value, a gray value. Saying 0, okay, it doesn't move in that direction. Anyhow, 100, it moves in the positive direction. Minus 100, it moves in the negative direction. Yeah? And then you do this for everything. And out of this bunch of gradients, you can compute a tensor, which is basically a mathematical construct which gives you an idea on how much something moves in the XY, or in the left, right, in the top, bottom, and in the back, front direction. And you can imagine it has a shape of a sphere, for example, if there is no directed movement in any of these directions. So there's no main movement. And you get a very small ellipse if it's totally moving upwards in that direction. And this information is then used to indirectly track the direction the macroscopic or the bundle of fibers of axons goes. Yeah, so that's about this diffusion-weighted imaging modality. Okay. Yeah, question?
Are there any publicly available data sets for MRI data or other volumetric data that you can input into this program? And specifically non-medical data or just sort of like weirder data sets that can be ingested into this program?
Yes. So to your first questions, if you search for DICOM and free or download, so DICOM, D-I-C-O-M, that's the medical image format widely used, but there are also others used in research projects. But yes, there are a couple of sites. For example, there's also the TCIH, the Tumor Cancer Imaging Archive, I guess, where there's a huge database of cases which you can download. And the second part of your question, MEVIS Lab can basically load a lot of different file formats, also JPEG and PNG, just 2D images. And of course, you could write your own importer. Yeah.
So there are many, many MRI archives. The largest and best curated one right now is the Internet Project. HCP, Project. And you have to get permission from them to get the data set from these thousands of subjects and build conclusions.
Thanks. Yeah. Yes, and another way you could look at are medical images, medical image challenges. So conferences around the world, like MICAI or so, they have yearly challenges to challenge the medical image community with a specific problem, like fiber tracking. Yeah, who has the best fiber tracking algorithm, the best segmentation, auto segmentation, fastest algorithm, and so on. So they have public challenges, and they provide test data on which you can train your algorithm, or train data on which you train your algorithm, and then you get test data on which you have to run it, and then you get a leaderboard, a public leaderboard, and you can apply for these challenges and then also get access to such data. Okay, thanks. So, time's nearly up. If there are no more questions.
And just feel free to come over and
Yeah,
our
of course.
thoughts.